it doesn't matter to me which of these versions we do. Once you've done one, I kind of feel like they're all the same. But when I say stuff like that, and then, we have a quiz on it, I've got like 2 or 3 people who are like, what the heck are we doing here? So I want to tell you that the homework was specifically made to show you all 3 possibilities. Or all 4, you know what I'm saying? I say, okay, now do it for when the thing sticks to it. Now do it for when the thing bounces off of it. Now do it for when the thing goes through it. Every one of those is on there. Just so you see the variety. If you know how to do it after you do the first one or the second one, I'm not asking you to continually do repetitive work. Some of you will understand what I mean by that. If you don't understand what I mean by that, well, you probably need to do the repetitive work. Does that make sense too? All right, let's get going. This problem isn't terrible. It's just long. So I need to redraw it because I don't have. So variations on a theme. All the energy in this problem comes from the bar here, retracted here. Now, what happens in these problems varies a little bit, but there's the collision where the bar is traveling at its maximum speed and comes into contact with the object. Now, this is one way these problems happen. This is the bar has the energy and delivers the energy to the object. And in this point of contact, there's generally only 2 things that can happen here. The box sticks to the bar, or the box doesn't stick to the bar. Those are your 2 options. But the bar usually continues afterwards. I want you to be aware that the bar continuing is often a part of the problem. Meaning they might say that the bar continues and makes some angle before coming to rest. They're telling you something about the bar, and you might not know what it is. So I want to do this problem 2 different ways. I want to do it the simplest way first, and then I'm going to add 2 wrinkles to it. Does that make sense? So let's start with the first one, and the easiest one is the bar sticks to the block and lifts the block up with it. All right? So let's start with this problem. There are a variety of questions associated with it. Let's talk about question number 1. Speed of the rod just before the collision. Speed of the rod just after the collision. Then the maximum height or the maximum angle attained by the rod after the collision. This is generally the questions that we tend to see in this kind of problem. And there are other side questions as well, and there's multiple ways to do this problem. A certain amount of liberty. But this is kind of what I want to look at for this particular question. So let's start by doing what I think is the obvious part, breaking this up and understanding what are the principal elements of physics that I think will serve us for this problem. I think question number 1 is a conservation of energy problem. The center of mass of the bar is going to descend, and therefore I see a clear change in height of one object within the problem before there's contact with anything else. What I'm trying to give you with that sentence is how you can tell which of the 3 things in our arsenal we should bring to bear. Is this forces? Is this energy? Is this momentum? The change in height suggests this is an energy problem. The fact that it's concentrating on one object suggests it's an energy problem. The 2 of those things together and the fact that I'm looking for a speed, all of that really suggests energy. So I'm going to apply the rules of energy to do part number 1. And in doing that, I'm going to recognize that I start with gravitational potential energy here. And that just before the collision, I'm going to have rotational kinetic energy. So when the word speed is put here, bless you, they're talking about angular speed. It's got to be angular speed. There's a fixed point of rotation here. So this object is rotating. Now they could ask for the linear speed of a part of the bar. If they're doing that, they're just adding more stuff for you to do. But the smoothest, the simplest problem is going from gravitational potential energy directly to rotational kinetic energy. And yeah, there's probably going to be a whole bunch of other language here. Like the bar being rotated about one end, that the bar is of uniform mass density. The bar has its center of mass at its center. They're going to probably say other stuff. I'm leaving all of that out because we're going to just treat this like a pretty generic problem. Let's use, for the length of the bar, something that's not capital L like I did yesterday, like a loser. Because capital L stands for angular momentum. And I ended up having it on the screen too much. So I thought maybe we'll choose something else for the length of the bar. Is that okay with you guys? And let's choose lowercase m for the mass of the box. And is uppercase m okay here for the mass of the bar? Just to differentiate them? I mean, we could downshift into numbers, but I'd prefer not to. So it seems to me that the amount of gravitational potential energy has got to be based on how low the center of the bar moves to. And that means that the center of the bar is going to be traveling a half of the length of the bar. We all good on that? Everybody understand why I'm making that argument? We've talked about it before. But that means the amount of gravitational potential energy in the problem will be mg d over 2. And that's the amount of gravitational potential energy. M for the mass of the bar, G obviously, and D over 2 because that's how far the center of the bar descends before contact with the block. Right? This represents the height of the center of mass below the lowest point that it travels to. Are we all good there? Am I good to keep moving? Excellent. Well, the next part is that this energy is being 100% converted to rotational kinetic energy, which we know to be 1/2 I omega squared. We're going to get omega from this. So, and that's what we're asked for, the speed. Now, we need I for the bar. They didn't say it, but I'm pretty sure I'm going to use 1/3 ml squared for the moment of inertia because this is a bar spun about its end. So 1/2 times 1/3 capital M D squared times omega squared. Now, if our job is to find omega, then we're pretty close to doing that now, right? Just do a little bit of algebra. And algebra is the least interesting part of this, but we're going to be reusing some of these things. So I'm going to cancel out the 1/2s because I got a half on both. I'm going to cancel out one of the D's, and I'm going to cancel out the M's. All of that can be canceled out. And just as a point of station keeping, this is what's left. I've been looking at some of your work, and one of the things I'm noticing is that sometimes the algebra becomes confused. So I just cancel out the things that were the same on both sides. This is what's left over. That might make it cleaner for you to be able to take and solve for omega. So now omega is going to be the square root of G over 3D. So this is how fast it's spinning. Any question about this or the work we've done to get here? There should be, but I'm not seeing it. Can somebody tell me what the mistake here is? Yes, ma'am? Good. Thank you. Look, it's 6th period. You know I have to check, right? We've gone over that. It's just, I need to check once in a while, see if we're all here together. There we go. So, that was question 1. How long does it take to do that part? 2 minutes? 3 minutes maybe? It's recognizing that it's conservation of energy, I think, that's going to take the longest, because you're going to be on the test. And remember, you're going to be moving from problem to problem to problem. So have you noticed one of the things I'm trying to do is tell you why I knew to use conservation of energy first. I'm trying to give you the starting points, the things to look for. Because the next one, the speed of the rod just after the collision. The word collision, I think, is what really signals that you're going to have to use conservation of momentum. So it's knowing that this is where conservation of momentum begins, just before the bar strikes the block, and understanding what kind of collision this is. In this case, the block is going to stick to the bar. So it's not really pictured so much here, but there's the moment just before the collision, and then there's the moment just after the collision where the block is also now moving, right? It hasn't been lifted up off the table yet, but there's like the split second before and a split second after. So it's hard to realize this, but a collision, in any sense of it, is just the instantaneous moment before contact and the instantaneous moment after contact. Because the moment that happens, the block starts to get lifted off the table, and some of that energy is being converted back into gravitational potential. So we're talking about, before that even happens, how much momentum is there before colliding and how much is there after. This is a conservation of angular momentum question. Linear momentum is not conserved in this question because of this point right here. There's an external force on the system, so that prevents there from being any conservation of linear momentum. And gravity is acting on the system. That also prevents there from being conservation of linear momentum. But there's conservation of angular momentum, which means the angular momentum of the bar just before the collision has to be equal to the angular momentum of the bar block system after the collision. Now, the collision portion of this problem isn't terrible, but you have to make a decision about how you want to treat the block. You can either treat the block as a point mass, or you can make the bar and block join together into one object that have a combined angular speed. You have a choice. You have to pick which one of these to do. You're going to get the same answer in the end. I am going to combine the bar and block into one object with a combined moment of inertia. That's how I intend to do this problem. Does everybody understand that there's a different way, though? So if you want to see the other way, be happy to show you, but let's do it my way first. I tend to like to join the things together when possible. So off to the side here, I want to recognize that when the bar and block are joined together, they will have a combined moment of inertia. The block I'm going to treat as a point mass. Does that make reasonable sense? Because we're rotating it so far away from its axis of rotation. And it has a mass of lowercase m and has a distance d away from the axis of rotation. So I'm going to treat that for the bar and that for the block and just add them together to have a combined moment of inertia. Is that good for everybody? All right. For the bar, I for the bar times omega for the bar. And then afterwards, I for the bar block times omega final. It's a conservation of angular momentum. So I set the angular momentum before the collision to the angular momentum after the collision. This is just like what we did before when we had, a situation with linear momentum. I still have 1/3 capital M d squared as my moment of inertia for the bar. But I also now have this square root of 3g over d. And nothing pretty about that, so I'm not going to worry about fixing it now. But that's going to equal, and this is going to start to get messy, 1/3 md squared plus lowercase md squared, all times omega final. trying to find ways to clean this up will be better for you. And there are some ways to clean this up. But I think we solve for the final velocity before we do so. So let's do that. Final velocity equals, I'm going to put the original velocity off to the side because we know that's a velocity. That was how fast it was traveling before. And I'm going to have the 1/3 md squared on the top there and 1/3 md squared plus md squared on the bottom. I see a way of simplifying this. Do you see a way of simplifying this? Get rid of all the d's? Think so? So that's what I'm going to do next. I'm going to get rid of all the d's. And that gives me 1/3 m over 1/3 m plus m, all times this 3g over d. There's not much you can do. I mean, there are little things. Like you can multiply top and bottom by 3 if you don't like the improper fraction. But if you're doing this on the AP exam, I'd stop here because there's really not much to do. All good to keep going? Now, this is a bit of a mess in that it's complicated, and we're going to be using it for the next part of the problem. But it's not terrible. So, are there any questions before I move on? The next part's not easy. All right. If we were just to this point, and this is all we had to worry about, believe it or not, joining the two masses together is easy for this portion of the collision, but it's harder for this portion of the collision. Because now we're done with the collision. The system's going to begin to rotate upwards. Do you realize that the velocity after the collision is going to be less than the velocity was before because this fraction has to be less than 1, right? It has to be. We've got something on the denominator that we don't have in the numerator, so it's going to have to be less than 1. So that means it's going to have less velocity, so it's not going to go all the way up to the 90 degrees from where it was dropped. Does everybody see what I'm saying? Or is that too much? All right, so in my picture here, the bar is going to gain a small amount, and we don't know how much, of gravitational potential energy because it's going to be lifted upwards. And the block is also going to be lifted upwards. So both the block and the middle of the bar both gain a certain amount of potential energy. Now, I think what I'm about to say is incredibly hard to discover as a student. But if you're discovering it, fantastic, you're the best. So let me ask you if you can do this. Could you write out, let's just say this angle ends up being theta, because we're supposed to find theta in this problem. Can you write two separate gravitational potential energies? One for the bar and one for the block. How would you write each of those? So this one's for the block, and this one's for the bar. I'm going to give you a hint. Treat the block like it's on a string that is L long, because you want both of these in terms of theta. Give you a second. So do we remember that this has to be mg d over 2 times 1 minus cosine theta? Remember how to do that? But for the block, it's going to be lowercase mg, not d over 2, because it's at the bottom of the block. I'm sorry, it's at the bottom of the bar. So it's mgd times 1 minus cosine theta. That okay? Not terrible, because it's about to get yucky. This was bad enough, but it's going to get really yucky. That has to be the total amount of potential energy after the collision. Has to be. That's the velocity just before it begins to swing upwards. So this becomes another conservation of energy question. The kinetic energy at the bottom has to equal the combined gravitational potential energy when it comes to rest. This is just terrible. This is going to look awful. And I feel bad to even have to write it out there, but I'm going to. 1/2 I. This has to be the moment of inertia of the block bar system. Yes, sir?
Wouldn't it still have kinetic energy though? When it's like swinging?
We're talking about the maximum angle it makes, so it's going to eventually come up to a stop, and then it'll come back. So we're talking about just how much, when all that energy's been converted, because that's going to be when it stops. Okay, remember how much of a mess the I is for this, right? Because it's two things combined together. So it's yucky. 1/3 capital M d squared plus lowercase m d squared. All times the velocity squared I don't want to do it either. Equals what a mess. Agreed, it's a mess? It's terrible. Just terrible. This is a tough one. It's a really tough one. Yeah, I don't think we have to solve for theta. Are you guys okay not solving for theta? We just stop right here? Because it's just algebra. But it's a lot of algebra. And they're not going to give you enough points in the algebra to make this worth it. Well, you're asking probably, Mr. Sheldon, is this really going to be on the exam? Yeah, sure, it could be. But if it's on the exam, they will do things to make this easier. Like, they won't have M and M be different things. Do you realize if the block and the bar are like M and 2M, that all the M's cancel out here? And once you realize stuff like that, you realize why they do that in the problem. So if it were me, I would make capital M, 3 times lowercase m, or something like that, because there's a 1/3 in there already. And stuff like that starts to, cancel out. So these are the kinds of things they will do to simplify the algebra without not at the expense of the physics that's here, to make the algebra simpler. But there's no way around the fact that some of this crap is just a lot of stuff. Yes, a D will cancel out here and there, and stuff like that's going to happen, but this is a mess. This is a lot, and I think they would not expect all that much of you from this point. They have never asked this question. They have asked the question where the block didn't stick to the rod. That question they've asked. So, as we look at possibilities, this is within the wheelhouse, but again, I think they would do stuff to make the math simpler, or they would just give you the numbers. You realize that they gave you the numbers, this one's much easier, because you can plug the numbers in way early. So, this problem. One of the choices here is to not have the block stick to the rod. That's a choice. That simplifies some things, but complicates others. when these two objects meet in the center, they stick together right at this point of contact. The way I describe it in the problem is they have Velcro on them. And so they have the opposite sides of Velcro, so they touch and meet in the middle. And when they meet in the middle, they start to spin. Does that make sense? Can you guys imagine this kind of scenario? This is a straightforward conservation of momentum question. In this question, I want you to think about two parts of this. First, we can talk about the linear momentum of the system. Before the collision, before this part takes place, when I have just those guys, the linear momentum of this system is 0. Do you guys see that to be true? Because they're in opposite directions. So after they collide, the linear momentum of this system has to remain 0. Because the momentum before was 0, so the momentum after is 0. But these two objects don't have 0 angular momentum. This problem requires that you think about the fact that when they meet in the middle, I think it's obvious to me that they're going to begin to spin when they meet and touch at that point. Is that pretty obvious to you guys? You can imagine that. So they must have had angular momentum before the collision because they have angular momentum after the collision. This is a problem where we're talking about the angular momentum of each of these objects adding together to be the angular momentum of the system after they stick together. This is a classic hockey puck problem. It's also what happens when two skaters meet on the ice or two ballerinas. It's been done a couple different ways, but usually the overarching portion of the problem is that you have two objects that have what appear to be purely linear momentum, and then after the collision, they have purely angular momentum. Does that make sense? Here's how you solve this problem. First, the point where they touch, that's the axis of rotation. So you start by identifying the axis of rotation in this problem. Next, these objects have angular momentum, but they are point masses traveling in a straight line before contact. So, in order to deal with that, you consider the split second before they touch. And in the split second before they touch, this mass had a velocity in this direction, and it was traveling in a straight line. Its angular momentum has to be r cross p. But this has to be r perpendicular times mv. Now, this part is tough, so let me kind of help you. I want you to imagine this straight line connecting the point of rotation with the center of the disk. We're trying to figure out the direction of rotation before the collision. Do you see that it's clockwise about that point? So, you guys see what I'm saying? So consider, again, it starts from here. It's going around that point. Like it's going this way around that point. Do you see that? I would argue that that's into the board for its direction of rotation. Do you follow that argument, or is that too much? Let me walk over. So, bear with me. Although that argument helps us explain that, we still have to come up with a way of expressing their angular momentum. We need stuff. So, like, this distance has to be the distance for r perpendicular. It's got to be the radius of the disk, because it's rotating about this point in the middle, but the center of mass of the disk is here. So I'm going to use a capital R to be the radius of the disk. And that means that our angular momentum will be capital R mv. And I'm going to extend that down here. This is also going to be capital R MV. And everything about the two disks is the same. So it's linear momentum. This one on top is going to be MV, and this one's linear momentum is going to be negative MV. They have complementary angular momentums. We all okay so far? I know it's a lot. I'm about to turn it up a bit. But that means the angular momentum of disk 1 plus the angular momentum of disk 2 will be 2 times RMV. Okay. Has to be equal to that. Get that out of my way. Come on, Mr. Shelton. There. So things equal to each other, and you can figure out how fast it's spinning after the collision. Jump ahead for a minute. If I have two disks spinning about a point on their edge, how would I calculate their angular momentum? Yeah?
You use the inertia of a disk, but you have to multiply by 2.
Okay, so we'll need the moment of inertia of a disk, and there are 2 of them. But we're going to have to do something else because they're not being spun about their center. We'll need to use the parallel axis theorem to move from the center of a disk to the edge and then multiply by 2 because there are 2 disks. There it is. Good job. Maybe I have the wrong idea. Maybe you guys did all ace that thing. Something like that. This represents the moment of inertia of a disk. I am shifting it 1 radius to move towards the edge. And how many of them are there? It's a lot, isn't it? But this, set those together. Now I'm just going to keep writing. You guys have to go. You're just solving that for omega now. That's how you do the homework question like this one. Let's start with the floor. So I'm not going to change it that much. I want to have a bar of length D and mass capital M that is at rest hanging vertically with a clear pivot point here. We good with that? And there is a box here traveling at velocity v and its mass lowercase m. Now, there are important things from the last question that are worth making sure you've seen, but I have choices on how to orchestrate this problem. Just like I had choices on how to orchestrate in this problem, I have choices. I could have the block stick to the rod, or I could have the block bounce off the rod, or I could have the block and rod continue to move in the direction they're moving now. Those are my choices. You guys follow me? Now, having the block stick to the rod adds a certain type of interesting complication in that the system joins together and creates a new moment of inertia. I find that to be something that's hard for students to do, which is why I like that question and why that's one we probably should do. It is the more difficult of the two questions. If the block doesn't stick to the rod, it makes our collision a little more complicated because we'll have a combination of an object with rotational angular momentum and an object that is still traveling in a straight line after the collision. So it doesn't matter which one of these we choose, there's complications all around. Everybody follow? I say we do the one where it sticks to the rod first and see where we go from there. Is that okay with you guys? So I'll remind you, G is in this direction. The rod is hanging there. So, and it currently is at its lowest position, so it has no gravitational potential energy. And if I really wanted to have fun with this question, I would start the block, say, over here, smashed up against some spring. So I could work in, conservation of energy with the block spring system. This introduces, a K into the problem needlessly for no useful purpose except to see if you understand that there's energy in the spring that is released and given to the block. But I'm going to forego that with the idea being that what we have to deal with is already enough. That okay with you guys? But consider, there's no reason not to bring stuff like this into the problem. No reason at all. So let's start with the problem just being about the block already having kinetic energy, and we're going to move the block in such a way that it strikes the rod. Let's go ahead and advance this question a few steps. I recognize that there'll be a point where the block and rod will have a point of contact. So let's just advance this guy a little bit to be right there. And then we'll have this other part of the system. Oops. That didn't help. Let's try that again. That good? You guys kind of see the steps of this question? This problem would be broken up into parts for you, which will help because there's a lot to do here. I see that there's a first part where we have to figure out the speed after the collision. So there's the part of the problem where these guys have stuck together. And there's the part of the problem just before they've gotten into contact. So here to here is, I think, question one. Where before the collision, just the block is moving, and after the collision, all of this is moving. But it hasn't quite started to swing upwards yet. Then I see another part we're trying to figure out the maximum angle made by the rod. The rod is going to swing in such a way that an angle theta is created here. The maximum angle will be when this system comes to rest, before it swings backwards. We all good? Now, this problem is relatively straightforward compared to the other problem in that it has fewer steps. because our system already has a certain amount of energy in it. And moreover, it already has a certain amount of angular momentum. So our question number one is to figure out the best way to deal with what's happening. Now, all of these problems bring with them a certain amount of, well, where should I start? And which one of my set of tools should I bring to bear? We only really have three major tools. We have Newton's laws, we have energy and work, and we have momentum and impulse. Work and impulse both involve force already. We know that force problems do a great job at telling us about forces and accelerations. Energy problems do a good job talking to us about displacements and velocities, where momentum problems generally do a good job with more than one object at once. They deal with collisions. I think this is a collision. I think it's a clear and obvious collision. Whenever I see a collision, I really think we should start with momentum and identify if momentum is conserved. So I think that's where we should start, because I see a collision between the box and the rod. So let's start there. First, you should ask yourself which type of momentum works best in the case of your problem. Is this going to be an angular momentum collision? Or just going to be a linear momentum collision? I think angular makes the most sense, and there's a couple of reasons why. The most important of which is that there's an external force acting on the system. This external force is going to act to make sure the rod doesn't leave this place. It can rotate about this place, but it won't leave this place. And because it's not going to leave this place, the linear momentum will not be conserved. When the block strikes the rod and pushes this way, there will be a push in this direction to keep the rod here. It might cause the rod to rotate, but the rod's not going to change location. This force can't apply a torque because it acts at the pivot point. This force can apply a torque because it acts some distance away from the pivot point. This is why the object pivots. Now, I'm not saying all of these things to you out loud because I'm trying to convince you that this is the right answer. I'm saying that for when it says justify your choice. Do you understand what I'm saying? You will have to justify why the system doesn't maintain or why it doesn't conserve linear momentum. And that's because it's experiencing an external force at the pivot point. I'm trying to give you those justification answers as much as I can. All right, so angular momentum. I believe the only thing with angular momentum before the collision is the block. So I'm going to set up my before and my after. And I know that in a collision question, I generally have a before and after, and I set them equal to each other. Before the collision, the only thing that has angular momentum is the box. I'm going to put a lowercase l because it's traveling in a straight line, and that suggests it's a point mass. So I'm going to be looking at its angular momentum relative to some point in space. Now I have to identify what that point is. I think we can all identify the point in space as being the pivot point here. We all agreed? That's the point at which these things interact. And that's the way the rod is fixed. So that seems like the right place to analyze the angular momentum of the block. Based on the fact that the block is going to make its closest approach right here, I'm going to use the fact that L can be written as R perpendicular MV. That we're going to use the point at which it contacts the rod as the value for R. In this problem, that's the length of the rod, isn't it? So I think the angular momentum of the system is going to be dm, why did I put L there? I meant to put V. After the collision, both the block and the rod have angular momentum. They have joined together, but you can treat this two different ways. And I want to start helping you guys bridge your notes together. You can treat these two objects as separate. and consider the angular momentum of the rod and the angular momentum of the block. Or you can combine their moment of inertia together and treat them as a single object. I think it's best to do the latter, to join the two objects together and treat them as a single object with a combined moment of inertia. But you don't have to. You can still treat them as separate masses. It's your call. But for this demonstration in front of the classroom, I'm going to recognize that I have one object that's going to have angular momentum L, and I'm going to use the capital L there. And I know that that means I omega. This will get me the angular speed of the system after the collision. Didn't specify which speed here, but angular speed seems to make the most sense here. Now, I am going to need the moment of inertia of the block bar system. The bar seems to be a bar rotated about one end, so I'm going to use 1/3 capital M d squared. I'm going to treat the block as a point mass, located at a distance d away from the pivot point. So that's going to be lowercase m d squared. And I'm going to use that as my moment of inertia of the system. They're both rotating about the same point and will both have the same combined angular speed. Any question about any of that? Yes, sir.
Might we be asked on the test to treat that not as a point mass, instead as like,
You could, but they'd have to give you the shape and parameters of the object. But it's very unlikely.
that seems a lot harder to have to do it on two axes.
It's going to add another thing in this sum. That's really all it is. Something where you would have had to have done the parallel axis theorem. And the parallel axis theorem would have probably already had this part in there. MD squared is the part you would have added to rotate it about some point away from the center of mass. So all you're going to have in there is whatever the moment of inertia of a square object is about its center. So we would need the side length. It's not as much as it sounds, but the problem is the side length there is much smaller than D. So we would find that whatever that small amount is going to be very little. And so realistically, it doesn't really actually contribute very much to the problem. Only if it contributed to the problem in a meaningful way would they include it. And it really doesn't here. You have no way of knowing that. But the telltale signs of that is that it's not being rotated about a point that's even remotely near the object itself. Does that make sense? All righty. So I think we can just do substitution here. And it seems to me that we now have a way of solving for the angular speed. So solve that for omega. Now look, this isn't pretty. And it appears to me that we could even get rid of one of the d's here. Do you guys see that? Could factor it out from the denominator and get that omega equals mv in the numerator and 1/3 md plus md in the denominator. Now, I don't think there's much of a reason to do what I'm about to do. I'm doing this demonstratively to show you something. If you stopped here, you'd probably get full credit for finding the angular speed. But if I just do a little bit more manipulation, do you see that this kind of fits the bill about linear speed and its relationship with angular speed? Right? Something like where r is the length of the rod. Do you guys kind of see that here? Just trying to point out that there are ways to know if you've done your algebra right and And this seems like a reasonable one. But either way, that's what we did. Now, yeah, we talked about this already, but I'll bring it up. If m was some multiple of capital M, do you realize the m's would cancel? And we'd be left with just some ratio here. It looks like if the block is moving faster, it has the bigger impact on this. If we could lighten this up, we get more speed out of it, don't we? So, and that's the kind of thing. The block has more inertia, and we make the bar not very heavy, you could probably get a lot more transfer of velocity to the bar. I don't think that's a surprise. When a heavy thing hits a light thing, the light thing moves more. That's what this says. All right. That's a lot of work, a lot of mathy math. Let's, moving on. Now, I did not point out the obvious other questions. What is the linear speed of the center of mass? What is the linear speed of the bottom of the rod? You do understand that those are problems that you could answer as well. You guys good with that? All right. We now have a system where both of these objects are stuck together and are moving, and we're being asked, what is the maximum angle here? You have to figure out which of the things we've talked about would make the most sense on working this problem out. Now, force could do this problem, right? If we use force, we could figure out what the net torque is on the system, and from there get an acceleration, and from there maybe figure out how far it moves before the system comes to rest. Except that would be extremely difficult. For anybody paying very close attention, you'd realize that to do that problem, the acceleration would be changing all the time. As it tends to move upwards, the amount of torque from gravity is changing. It would be a hard way to do the problem. I don't want to do it that way. But I do notice that the center of mass of this system is changing height. Do you notice that? I think we could probably do this problem in terms of conservation of energy. The system appears to have kinetic energy after the collision, and if it comes to rest, it's probably got potential energy after it comes to rest. So I think this max angle occurs when the system has converted all the kinetic energy into potential energy. You guys okay with that? All righty. You'll notice that's not a problem that has anything to do with momentum, but we're probably going to need this velocity. That's going to tell us how much kinetic energy we have. Now, I want to focus for a minute on the other part. Kinetic energy is going to be simple, 1/2 I omega squared. We already derived an expression for I, and we just found omega. So I know that we already have those things. But when the system swings upwards, it's going to store gravitational potential energy. I think we should spend a few minutes figuring out an expression for the gravitational potential energy. All right, you guys have two ways to do this. I don't think you know that you have two ways to do this, but you do. One way to do this is to figure out where the center of mass of this system is. And then from there, figure out how high the center of mass is lifted. The second way to do this is to figure out how high the box is lifted and how high the center of mass of the rod is lifted, and add those two things together. You'll have to choose which method to do. I would choose the latter. I would figure out the amount of gravitational potential energy for the bar and the amount of gravitational potential energy for the block. They're both going to be some form of MGH. You just have to figure out how to deal with the angle and H. And you should have that answer at the ready, because we've done this before. So I want to give you a second and see if you guys can put these two things together, because we've done both of these before. So it seems like something you should be able to do without my assistance. All right, I'm going to stop everybody here. Mostly because we just don't have that much time, and only about 4 of you appear to be like talking it out with somebody else, which is fine. Look, this should be pretty straightforward. The block is at the bottom of the rod. The rod is a distance d long. If it moves upwards some angle theta, that has got to be how much gravitational potential energy the block has. Just the block by itself. Yep.
Sorry if I'm being like an idiot, but why is it 1 minus cosine theta, not just cosine theta? Forgot as well.
Now, what AP wants to know is not just that you have this, because that's something, but that's geometry, that's not physics. They do want to know if you understand the relationship between the height and the angle. That shows up enough on the exam where it's worth us understanding, or at least putting it down there. But did you know to say mg d over 2 times 1 minus cosine theta for the bar? Because we're talking about lifting up the center of mass of the bar, and that's at its middle. So did you do that? That makes a difference. Which means the total amount of gravitational potential energy is mg d over 2 times 1 minus cosine theta plus lowercase mg d times 1 minus cosine theta. That's how much gravitational potential energy there will be in terms of theta. Now, we're going to set that equal to the amount of kinetic energy the system has. And whoa, there's a lot to do there, isn't there? Let's consider 1/2 I. We have an expression for I that we already solved for. 1/3 md squared plus lowercase md squared, moment of inertia, times omega squared. Wow, that was a long time ago, and I've had to do a lot of explaining since then. There's my angular velocity, and we have to square it. Okay. Wow. Okay. I know you're hurriedly trying to write all that down, but you understand that they're not going to do this on the exam. They're going to tell you that the mass is 100 grams and the mass of the block is 20 grams and it was moving at 3 meters per second. Or they're going to do something else that will make this compact itself. Something where the m's are all multiples of each other. Now, there are things that cancel out here. I don't know if you see that, but there are. The d's cancel out on this side. Because I have a d squared in the denominator there and a d squared in the denominator there. I also have a 1/3 m plus m on the numerator here and 1/3 m plus m in the denominator there. There are things that cancel out. But there's a heck of a lot that doesn't. And so this would be work to isolate theta. You guys follow that okay? So you're noticing that although this is a simpler problem than the one we had in the other class, I don't think the word simple is the right word to apply here. Simpler? Sure. This is a 2-part problem. The only difference between this problem and the one we did in 6th period is the kinetic energy came from the bar being pulled sideways first and released. So they had an expression for the kinetic energy based on the height of the bar before the system began moving. It's the only difference. It's a small permutation on the same problem. Now, I hear you guys shuffling the whole pack-up thing, but I want you to know about something that we talked about in 6th period that you should look at tonight because we ran out of time. We did this problem, or at least we set up this problem, and it's one of your homework questions. So if you want to see a sample homework question, this is it. In homework, I talk about 2 pucks being fired towards each other, but the pucks have Velcro around their edges. so that when they meet in the middle, they stick together and start to spin. This is a textbook example question that you guys should look at. The two pucks have clear linear momentum, but they also have angular momentum about this point. I go into great depth about the fact that their linear momentums cancel, because this one's traveling in the positive direction and this one's traveling in the negative direction. So the momentum of the system is going to be 0. But the angular momentum of the system is not 0, because their angular momentums are in the same direction. This puck travels past this point, so it's rotating this way about that point. And this puck travels past that point, so it's rotating this way about that point. They have complementary angular momentums. We all follow? We get almost to the solution at the end of 6th period in this question. You should definitely look at it, okay? All right. Thank you.
I remember the formula. Do I remember how to get to it? No, but I remember.
It's okay.
I remember that -1 -, like hard.
All right. So here's what we're gonna do. We're gonna do it because I want to make sure that I've done due diligence. I made sure I used the same size line here so that this is accurate and detailed. And if we're imagining that the box is at the bottom of this, then the box has been lifted this height, correct? Okay. This, in our example, is D, and this is D, and this is theta. So I'd argue that this is the adjacent side. So cosine of theta is going to be A over D. So the adjacent side is D cosine theta. We don't want D. We want H, which is D minus A, which has to be D minus D cosine theta, which is D times 1 minus cosine theta. And yes, I believe this is what I'm memorizing. Okay? We all follow? Because the reason why I would never suggest that any student is an idiot is because we all forget things, and I'm pretty sure if I asked anybody in this room to prove it, I'd probably have a less than 50% shot at getting it out of you all. And I don't want to know who could or couldn't do this. I want to know that you've memorized it now and you don't have to do this for the test. Because you'll lose a point for putting just cosine theta, and it's not worth losing that point.